This is Chapter 4, Part 3, Basic Logic Gates. In this video, we're going to learn how to convert Boolean expressions into circuit designs. We're going to implement circuits either with all NAND gates or all NOR gates. And we're going to discuss bubble-to-bubble logic representations and how they are used. We're going to talk about logic implementation of Boolean expressions using the following elements: AND gates, OR gates, and inverters. A digital circuit is just the logical implementation of a Boolean expression. But in practice, these digital logic circuits are implemented typically using NAND gates. And in fact, all the logic implementations of Boolean expressions can be realized with only NAND gates, because a NAND gate can be configured either as an inverter and or OR gate. So what do we mean? So here are the NAND gate implementations of the three basic gates. The three basic gates are the inverter, the AND gate, and the OR gate. And as we learned earlier, the AND gate is the ALL gate, you say ALL, and the OR gate is the ANY. Okay, let's look at these NAND gate implementations. Well, we know that this one here, because the two inputs are tied together, that anytime A is a 1, both the inputs are a 1 there and the output's going to be a low. So it inverts a 1 to a 0. And then any other, the alternate representation says that for this NAND gate, 0, 0, this says that any low gives a high. So anytime you have a 0 there, you're going to get a 1 right here. So this is just an inverter. That's all it does. Inverts the input. A is equal to B bar. Or let's write B is equal to A bar. That's better. Okay. So let's look at the second one here. We have a AND gate with a bubble on the output, which means it's a NAND gate. And then we invert it one more time. This is just simply an inverter. So it's a NAND gate. We invert the output. There's a bubble here and a bubble here. It just becomes an AND gate again. So what we're left with is an AND gate. A, B, C. So C is equal to A times B, or A and B. Okay, what's this one here? Well, this one here is 3 NAND gates, because this is the alternate representation right here of a NAND gate. So the first NAND gate is just an inverter. So it's inverting A to A bar. So this is A bar here. This is inverting B to B bar, and this says any low gives a high. So you can think about it as this whole grouping of 3 gates right here performs the function of an OR gate. So this is a NAND gate implementation of an OR gate, where you have inputs A, B, and C. So that's an OR gate or an ANY. So the output C is equal to, let's do this. C is equal to A plus B. Okay, so we've implemented the 3 basic gates, inverter, AND, and OR, with NAND gates. So we can use NAND gates to do anything we want in these Boolean implementations. Like we just discussed, we can implement any circuit with AND gates and OR gates and inverters. Here's an example of a circuit that we've implemented using this Boolean expression right here. This Boolean expression is A, B, C bar plus A plus B, the whole sum term inverted, plus, and then add the two together. So we take C bar times AB, and we get ABC bar. So that's this piece right here. So this AND gate implements the ABC bar. This is a any or an OR. This says any high, gives a high, but A plus B. A plus B is right here, and that's the second term without the inversion. So we invert it right here, and we get the A plus B bar. And this says that you're going to sum these two terms together, ABC bar. This sum term right here says that we're going to add ABC bar right here with A plus B, the whole term inverted right here, and then we get the output F. So this is the logic implementation of this Boolean expression ABC bar plus A plus B bracketed, the whole output inverted. So this is the logical expression. We have two OR gates and an AND gate and two inverters. Okay, let's look at this circuit right here. There's another example. Here it says the Boolean expression is equal to F of ABC is equal to A bar B plus AC plus bracket A bar plus C bar. So how would we implement that? Well, the first gate, this first run right here, we take the not, or the inversion of A naught, times B. So that's what this is right here. So we get A naught times B. The second term is AC. So we have A times C, and that's his second term right here, AC. And the third term is A bar plus C bar. Well, we've got A bar right here. This is an any or an OR gate, and then we take the C, invert it, and we get C bar. So this term right here is equal to A bar plus C bar. So what do we do with these three terms? Well, we sum them together. A bar B plus AC plus bracket A bar plus C bar. So we sum them together with this gate right here, and it equals the function. So again, this is the logic implementation right here of this Boolean expression right here. This is the logic implementation. We've seen this circuit before. This is a majority circuit. And what this circuit says that anytime you have a majority of ones, and in this case we have 3 variables with 8 combinations, anytime you have 2 or more ones, or a majority of ones, the output's going to be a 1. So it's in this case, this case, this case, and this case. So that is equal to the minterm sum of 3, 5, 6, and 7. 3, 5, 6, 7. Okay, here's a circuit implementation of this Boolean expression. Again, this is the minterm product terms for 3, 5, 6, 7. The first one is A bar B, C. So we have A, we invert it, so we have A bar times B times C. So we get A bar B, C. That's the first one. The second one, we get A, B bar C. We have A, B bar C, so we have A. And then we have B, and we invert it to B bar, and then C. So this is A, B bar C. The third term, A, B, C bar. We have A, B, and then C bar. So we have A, B, C bar. And the final term, A, B, C. All non-inverted input variables. So we have A, B, and C, and the output's A, B, C. What do we do with those? We sum them all in an OR gate. So the output function is equal to these 4 terms summed together. And remember, we said this was the sum of product terms. These are the 4 product terms, and then we sum them all together. So we have 4 3-input AND gates, 1 4-input OR gate, and 3 inverters to implement this circuit. Well, we know from our Carnot maps that we can simplify this expression. And so that's what we did. We took this truth table and we mapped the ones on this Carnot map, and we minimized to only 3 product terms. So this is a minimal implementation of the majority circuit. And the way that translates is we have fewer gates, and fewer gates are better. Okay, so we have the first term is AC. This is AC. The second term is BC. So we have C here and B here. So we have BC. The third term is AB. We have A and then B. So that's the third term, and we sum those together, and this is the function we get. Much simpler than this one here. This was the non-minimized circuit. It had 5 gates and 3 inverters. This one has 4 gates, 3 and 1 OR, and no inverters. So a much simpler implementation. Fewer gates, less logic, more real estate, less power. All good things. Okay, well, let's map the zeros of this function, this same majority circuit function. And the zeros are mapped to these 3 sum terms, as we showed in our previous section on Carnot maps. We have 3 2 cubes here. So we have the first term we have is B plus C, the second term is A plus B, and the third term is A plus C. And this is the POS, or product of sums form. Okay, and we're mapping the zeros. So let's implement this circuit right here. Okay, let's do the first one here. This first one just says B plus C, so we use an OR gate. So we have B plus C, and that's B plus C right there. So that's the first sum term. Let's look at the second sum term. The second sum term is A plus B. So we have A and we have B, and we sum those together and we get A plus B. Okay, so that's the second term. The third term is A plus C. So we have A plus C, and we have A plus C. Okay, and then what do? We multiply these 3 terms together with an AND gate. So these 3 terms are multiplied, and we're left with the output function F. So this is the product of sums form for that same majority circuit. Redisplaying these 2 circuit implementations. The first one for the ones, or the SOP form, is this one right here. And then the second circuit for the POS, where we map the zeros, is this circuit right here. You can see that the circle implementation is different, the gates are different, but the output function, the output value as a function of the input variables, is identical. So these are the 2 implementations of the majority circuit, and they create the same output for the same combination of inputs. So they're the same circuit, although you implement them differently. One's an SOP form, mapping the ones, and the other is a POS form, mapping the zeros. Okay, now we're going to talk about a concept called bubble to bubble. When we look at a gate representation, whether it's this is an AND gate right here, or an alternate representation of an AND gate, which is, as we showed before, is this right here. The inputs have bubbles, or the outputs have bubbles, or the inputs and the outputs have bubbles. And what bubble to bubble logic says, in most cases where you can, when you have an output bubble, make sure you connect it to an input bubble. Well, there's no input bubble here. So we've kind of violated that rule with this implementation. This is an AND gate, this is an AND gate. This output NAND gate has a bubble, but there's no bubble over here. So we're not connecting bubble to bubble. And bubble to bubble says, not only do you connect bubbles together, but if you don't have bubbles, you connect the non-bubbles together. So if you have 2 circuit implementations, you have an output gate like this, that's high, and then you have an input that's like an OR gate. There's no bubble. You connect non-bubbles to non-bubbles, and you connect bubbles to bubbles. Okay, why do we do that? Well, it's to understand the logic flow. If we were trying to fill out the truth table for this particular function, it would be fairly difficult because we don't really know. This particular logic gate right here doesn't tell us what do I have to do to make this output function a 1. What do I have to do to make this a 1? Well, this logic gate right here is telling us what we have to do to make this output a 0. It says all inputs high, 1, 1, give us a 0. Well, logically, what do we got to do to get it to be a 1? Well, it's not entirely obvious when we look at this circuit. A better way to do it is implement that with bubble-to-bubble logic like this. We have a NAND gate. We have a NAND gate. These are the same two NAND gates. And this is a NAND gate also. Remember, this is the alternate representation of that same NAND gate. So when we do it this way, we can connect this output bubble to this input bubble. We can connect this output bubble to this input bubble. So we're connected bubbles to bubbles, okay? And what does that do for us? Well, if we look at this gate and we're trying to understand what it's doing, and we're trying to fill in the truth table here, what does it tell us? How do I get a 1 on the output here? The way I get a 1 on the output, this is an any, I have to have either a 0 here, any low gives a high, or a 0 here. So anytime I have a 0 here or a 0 here, I'm going to get 1 out here. Okay? Let's do the first one here. How do I get a 0 here? Well, to get a 0 here, this says all highs give a low or a 0. So how do I get all highs? 1, 1. A and B are both a 1. All highs give a 0. Okay, I have a 0. That's what I want. I want a 0. Any 0 gives me a 1. So what did I have to do to get this 1? I had to have both A and B a 1. So let's go down, and whenever A and B are both 1s, right here we have a 1, 1, 1, 1. Okay, let's look at this. Let's look at the second input to this gate. Or this says we can have a 0 here. So if we have a 0 there on the other input to this NAND gate, we can have a 1 on the output. So how do we get a 0 here? Or how do we get a 0 here? Well, to get a 0 here, this says all inputs high, so C, D. 1, 1 will give us a 0, and when we get a 0 here, any 0 gives a 1. So anytime C and D are both 1, we're going to get a 1 out. Or C and D both 1. C and D are both 1 right there. And C and D are both 1 right there. And C and D are both 1 right there. Okay? And we don't care about A and B on this side right here. Okay? So this is the truth table. And of course, everything else in here is a 0. We've created the truth table, or we've been able to analyze the circuit to create the truth table, because logically, when we look at this circuit, it makes logical sense. When we look at it this way, it doesn't, because it doesn't really describe logically what's going on. You have to kind of understand a little bit about how this AND gate works here, which is really saying that any low is going to give a high. But when you have a bunch of these all chained in a circuit, it makes it really difficult to understand. And that's why we do bubble-to-bubble logic. When you do bubble-to-bubble logic and you use a correct logic symbol for that particular gate, it makes it much easier to understand the operation of the circuit. Okay. Now, when we have an SOP representation, or sum of products representation, for a circuit that we've implemented, and this is the Boolean expression down here for the function equals AB plus CD. Well, we have 2 AND gates and an OR gate, or 2 OR gates and an AND gate. Really, we'd like to implement this with NAND gates. And one really major reason why you want to use NAND gates is because to implement a NAND gate, it takes less transistors than it does to implement a AND gate. And the reason is, electrically, to implement an AND gate, you're going to get a natural NAND gate from the electrical circuits, and then you'll have to create another inverter to get it back to AND again. So to create an AND gate, you have to add another stage of inversion. So it takes more transistors, more gates, more power. So the natural gate implementation from a circuit implementation standpoint is the NAND gate. So that's why most of the time you use NAND gates for circuit implementations. So how do we convert an SOP form that we create right out of our truth table, our Boolean expression, and we're assuming this is a minimized Boolean expression? How do we create the NAND gate implementations? Well, all we do is add bubbles on the output on the first stage and bubbles on the input on the second stage. So what is this gate? Well, that's a NAND, that's a NAND, and this is the alternate representation of a NAND. So all we had to do is put a bubble here and a bubble here and a bubble here and a bubble here, and we've changed from AND and OR gates to NAND gates, and we didn't have to do anything except replace the AND gates and the OR gate with NAND gates. Fairly simple. How do we do it for a POS form, or product of sums? Well, here we have a OR gate, or an any gate, and we have an AND. Okay, and this is the Boolean expression right here. So how do we, for a POS form, how do we implement this particular POS using NOR logic? Again, when we talk about circuit implementation of a NOR gate, when you implement an OR gate again, when you do an OR gate inside for the transistor implementation, you get a natural inversion on the output of your OR gate, and you have to create another inverter on the output of that NOR gate to get you back to an OR gate again. So again, you have to add extra circuitry to get to an OR gate. And as was shown before, it's the same with the AND gate. Okay, so how do we get back to how do we implement this OR AND, which is what we want to do, and use only NOR gates? Okay, all we do is we add bubbles on the outputs and bubbles on the inputs. And of course, we know from our previous presentation that this is a representation for the alternate representation of a NOR gate. These are NOR gates. This is the alternate representation of a NOR gate. Okay, and that's why we did that. And how do we implement it? We just took this OR gate and we added a bubble on the output, and the AND gate here, we had bubble on the input, and voila, we've created NOR gates. Okay, so net, here's what we have. We converted an SOP form, sum of products form, from an AND OR to a NAND implementation, which is still an SOP form, just by changing the AND gates to NAND gates and changing the OR gate to a NAND gate. And logically, they are equivalent. Very simple. The same with the POS. For the OR AND POS implementation, all we had to do was just replace the OR AND gate with all NOR gates. And we get the same implementation with fewer output gates. So bottom line is you can implement a function with the ones of the function in the SOP form using only NAND gates, or you can implement it using the POS, or mapping the zeros of the function, only using NOR gates. Okay, let's look at another example of bubble-to-bubble logic. And then there's one variation that I'd like to talk about. This is a Boolean expression. And these are the sum. This is the min-term sums, 0 through 5, 8 through 11, and 15. And that's shown on this Carnot map here. Well, we mapped all the ones in the function, and this was the reduced Boolean expression. Oops, sorry. This was the reduced Boolean expression we got, and we implemented it in the SOP form. Okay, and this is what we got. We got the first term is ACD, this one right here. This is ACD. The second term is A bar, C bar. There's A bar right here, and there's C bar right there. So this is A bar, C bar. A bar, C bar. And this is ACD. And the third term is just B bar. We take B and we invert B. So this is B bar. Okay, this is an SOP form. How do we convert this to bubble to bubble? Well, it's easy on the NAND gate, on the AND gates right here. We just put a bubble and this is an AND gate. We put a bubble, this becomes a NAND gate. Well, on the third level here, in the third input, there's no NAND gate. But the rule says you got to invert everything on the first level. So we have to add another inverter in here. Okay. And this other inverter creates a bubble on the first layer, and then connected to this bubble on the third input to this NAND gate. So the thing is, again, now you have to invert the outputs on the first layer, and in this case we have to add another inverter to invert the output. So it's very important. If you forget that, it's not going to work. Okay. So if you look at this net, we go down to implementing this particular function. This is a 3-input NAND gate, a 3-input NAND gate, a 3-input NAND gate, and then we have 2 inverters. But if we look at this right here, B is inverted to B bar, and then B bar goes back to B again. So we don't need these inverters, net. So it's just B going directly in. But we put the second inverter in just to show when you have to invert the output on the first level, connect to the second level bubble. Okay, that's a subtle point, and you can't forget that. You have to invert everything on the first layer, and all the outputs on the first layer and all the inputs on the second level. Sorry. Okay, let's do an OR AND to NOR conversion. Let's do another one here. We have, this is the max term representation over the zeros, 6, 7, 12 through 14, and that's what we have. The zeros in this Carnell map. We reduce the function, and we get 3 sum terms in our reduced implementation, and those 3 sum terms are shown here. This is the first one. This one right here. This is A bar plus B bar plus C. Okay, and that's this one right here. This second sum term is A plus B bar plus C bar. Plus B bar plus C bar. And that's this second one right here. The third one is B bar plus C bar plus D. So this is B bar. There's B bar right there. Plus C bar plus D. There's C bar right down there, and then D plus D. And you multiply those all together and you get the output F. Well, let's convert this to NOR logic. Okay? So we have all these gates on the first level. Okay, so you invert all the outputs on the first level. There's 1, 2, and 3. And so you've created NOR gates on the first level. This is the alternate representation of a NOR gate. And so this is you take the 3-input AND gate and you add bubbles to it, and this becomes a NOR gate. Okay, so you have 1, 2, 3, 4 3-input NOR gates and 3 inverters to implement this function right here. Okay, so this is the bubble-to-bubble case for the NOR gate implementation. So again, it doesn't really matter how you implement these functions. You're going to get a minimal implementation when you either use NAND gates or NOR gates. Generally, the NAND gate is more common in FPGAs, gate arrays. You have more NAND gates available than NOR gates. So it just depends on your circuitry that you're going to use to implement your particular functions. Maybe the NOR gates are a little more expensive than the NAND gates, but from a size and power and number of gates, implementation wise, you can go either way. You know, the NOR gate implementation may have fewer gates, so you can compare the two, but typically most people use NAND gate implementations. So what did we learn in this chapter? Well, this is the video. This is the last part in basic gates, and what we learned was the basic gates that are used to implement a digital logic circuits, and it's basically the inverter and NOR functions. And those and OR functions can be implemented either using NAND gates or NOR gates. And the NAND gate or the NOR gate can be used to represent or inversion. We implemented both sum of products and product of sum expressions using either NAND or NOR logic gates. And we saw the importance of alternate representation of logic gates, because in order to understand the circuit that we've designed or somebody else has designed, if you use the alternate representation that displays the actual circuit flow of the logic that you designed, it makes it so much easier to understand what's going on, especially when you're troubleshooting a logic design, trying to make sure that the gates are connected correctly, or you have a flaw in your logic design, whatever problem that you might have. Also, we talked about bubble-to-bubble logic and why it's important, and why most designers use bubble-to-bubble logic with the alternate gate representations to help you fully understand the logic flow for a particular logic implementation. I hope you enjoyed the video.